Okay, good morning, everyone. I hope you're doing fine. So let me know if you can hear me. I think the stream should be up. Um, okay, yeah, good, excellent, thank you. I can see a couple of thumbs up, and people telling me that they can hear me. Excellent, very good. So what are we going to talk about today? We're going to do a few more exercises on on solving Newton's laws problems, and then starting next week, we're going to add progressively more complicated aspects to this to these problems. So before we get started, just a recap where we left off. We were talking about types of forces, tension. So we're going to add friction and springs to that today, and then we're going to solve some problems with Newton's laws. So tension, we were talking about this problem of a tightrope walker walking from the Eiffel Tower here on this tightrope, and so the question is now what is the tension in this rope, or in this cable more likely, due to the weight of that tightrope walker. And so we can turn this into a little bit of a diagram. You can draw the forces, the free body diagram. So let's look at what the forces are. So we've got the tension on the right side here. We've got the tension along the left side, and with tension, it is always a force that is pulling, and it is along the direction of the rope. So in this case, the tension has to be along the direction of the rope at 5 degrees away from the horizontal. And the same thing on the right hand side. The other force working on the tightrope walker, sorry, blanked there for a moment, on the tightrope walker is of course the weight, and the weight is always vertically down. So now what we do is we pick our XY coordinate system in a way that's convenient for us. And so what we're going to do here is pick it just with X horizontal and with Y vertical. So W, the weight, is going to be along the Y direction only, and the tension on the right side and on the left side are going to have components both in the X and in the Y direction. In fact, I don't have that drawing, but we can solve this problem. You see, I forgot to pull up my notes on my own screen here. So we can solve this problem. So let's assume that that the weight of this tightrope walker is 70 kilograms. So sorry, I misspoke. The mass of the tightrope walker is 70 kilograms. The weight of the tightrope walker is 70 kilograms times the acceleration due to gravity, so times 9.8 meters per second squared. So that's the weight is determined by the mass. So what we're going to do now is look at this free body diagram. I'm going to draw this again here. So the tightrope walker. So we've got our free body diagram with the weight down, mass times gravitational acceleration. So the Y component is minus 70 kilograms times 9.8 meters per second squared. And then we've got two components, or two pieces to the tension. So there's the tension to the right here, there's the tension to the left on this side. Both of those will have a X component, TLX, and a Y component. I'm going to actually draw that over here, TLY. So once I've decomposed it into an X and a Y component, I'm going to make sure to cross out the original tension vector. So then for the right side, we have something similar, the X component for the tension on the right side. And we're going to have, I'm going to draw this in the extension here, we're going to have a y component for the tension to the right. So of course these two vectors, they really add up to be able, they add up to form a full y component of both the left and the right part of the tension. So let's now write down, let's assume that this tightrope walker is walking at a constant velocity. So the acceleration is equal to 0. So constant velocity, or maybe even the tightrope walker is at rest. So if the acceleration is 0, that means that the acceleration in x is 0 and the acceleration in y will be equal to 0. The acceleration in x is 0 means that the net force in x is equal to 0. And the net force in x is TLx plus TLy. No, what am I saying? TRx. So that's the net component of the x of that's the x component of the net force. And so since only the tension has components along the x direction, that is going to give us the sum of those two x components. And so that will mean that TLx must be equal to minus TRx. Okay. The y component now, that tells us that the net force in the y direction must be equal to 0. And that is equal to TLy plus TLTR y minus m times g. So now the next step is, how do we relate these two equations to or how do we relate these two equations to each other? Or how do we relate the x components of the tension to the y components of the tension? Well, we know, of course, what this angle is. This is 5 degrees, or let's just call it theta for a more generic solution to the problem. So if this is theta, that means that TRy divided by TRx must be equal to the tangent of that angle theta. So that gives us a connection between TRy and TRx. And since the same thing is true for TLx and TLy, it will also be equal to the same angle theta, we can actually see that this will mean that TLy must be equal to TRy. And in fact, the magnitude of TL must be equal to the magnitude of TR. So if we go back to the drawing over here, essentially you could have predicted this from the symmetry in the problem as well. If there's the same angle on the right side as the angle on the left hand side, then the tension has to be of the same magnitude so that the horizontal components will cancel out. This would be different, of course, if the acceleration is not equal to 0. So if the tightrope walker is speeding up or slowing down. So if this is the case, now we can go back here. We can see that that is equal to 0. That the sum of the tension in the y direction and the mass times the acceleration in the y direction, that must be 0. So that means that the tension, or 2 times the tension, for example, in the y direction for the left component, must be equal to m times g. And the tension in the y direction is the total tension, which we'll call just capital T, times the sine of theta. That's equal to m times g. So the tension must be m times g over 2 times the sine of theta. So now let's plug in some numbers. If we plug in the 70 kilograms times 9.8 meters per second squared divided by 2 times the sine of 5 degrees, then we'll find that this is 3,930 newtons. So that's a force. That's the tension. We've calculated the tension. Is this a large tension? Well, let's put this into context, and let's compare it with the other force that we know here. The other force we know is the weight, and that's just the 70 kilograms times 9.8 meters per second squared, and that is 686 newtons. So what you can see is that the tension is actually a lot larger than the weight. So, and this is something that, you know, as a physicist, we would look at this and would wonder, well, why is this such a large force when it's really just caused by a weight that's so much smaller? There's a factor, what is this? A factor 5 difference here, or maybe not quite a factor 5. Actually, it's more than a factor 5, is it? Yeah. So there's a large difference here. And this is caused by the fact that we have this sine of a small angle here. So if we now think about this as a function, as the tension as a function of the angle, we could plot that function, right? We could plot the tension versus the angle theta, and you know, we could theoretically go up to, let's say, 90 degrees here, and maybe we'll have, let's say, 45 degrees here. For 90 degrees, and let's write this tension here, since it's proportional to 1 over the sine of theta. Let's just write this as 1 over the sine of theta. So the tension is proportional to that anyway, but I'm going to plot 1 over the sine of theta. The sine of 90 degrees is 1, so 1 over the sine of 90 degrees is 1. The sine of 45 degrees is 1 over square root of 2, so square root of 2 will be the value at 45 degrees. And you can see that this actually goes up sharply, and there's an asymptote at theta equals 0 degrees. And this is, of course, what explains why this force, this tension, is so large at small angles. We're at 5 degrees here. Well, we got to go all the way up here, and this would give us, let's say, a factor of 5 or a factor of 10, which is why that actually it will be, let's say it's a factor of 10. So that will cause this mass times gravitational acceleration to become a very large tension. And this is actually the insight that we want to get from solving problems in symbolic notation first, before we actually plug in the numbers. Because now we can see, how does the tension depend on the angle? Well, it depends on the angle as a 1 over sine theta dependence. How does it depend on the mass? Well, it depends linearly on the mass. If the tightrope walker, if there were 2 tightrope walkers, we get 2 times 70 kilograms. If the mass doubles, then the tension will just double. But if the angle is only half, then it actually will change. Not the tension won't change by a factor of 2. It will change like the ratio of 1 over sine theta when you change the angle to half of its value. So that dependence is actually different. And of course, we can now apply this in the opposite direction as well. So instead of calculating what the tension is based on a certain mass, we can now think about this as there's a transverse force, transverse to the direction of the cable here. And that small transverse force can cause a large tension. So one example where you would be able to use that is, let's say you're stuck with your car in the mud. You can tie a rope or a chain between a tree and your car, and with just a small transverse force, you'll get an amplification or a magnification of that force to the tension, and you might be able to pull your car loose out of the mud just by pushing sideways against this cable. Of course, it relies on this angle theta being small. So having a small theta will cause an amplification or a magnification of your force that is applied in the transverse direction. As soon as this angle, of course, becomes large, then you lose that magnification. Okay, so that's one example, of course, of solving problems with free body diagrams, but also an example of how to use tension and how to think about tension. So think about it as always pulling along the direction of the wire of the rope. A next type of force that we still need to talk about is springs. Again, springs, as I already mentioned, is a very important concept. Essentially, every force in nature can be approximated as a spring force, or maybe not every force, but virtually every force in nature can be approximated as a spring force within at least a small range of motion around the equilibrium. So think of a spring as the thing that is a restoring force that tries to bring your object closer to its equilibrium. So for spring forces, there's a expression that gives the force in terms of the displacement from equilibrium. So this is the displacement from equilibrium. And that force will be proportional to the displacement with a proportionality constant K. K is the spring constant. And the direction will be such that if the displacement points in one direction, let's say I have my spring, which has an equilibrium position here, well, I stretch out the spring until it's this long. So my displacement delta x is in this direction towards the right. That means the force will be in the opposite direction because it will try to restore that spring to its original length. So the force will be negative K times delta x. It will be along the direction of the displacement, but it will be pointing in the opposite sense. So this is indeed known as Hooke's law for Hooke, who came up with that realization. There's of course, there's many ways in which we can actually use this equilibrium. So in this case, I'm looking at this as something that is essentially moving sideways. One way to think about this as well could be, let's say we have a spring that is hanging from the ceiling and there's a mass hanging from that spring already. So right now, this spring is in equilibrium. If I, even though of course on the spring there's two forces operating, there's a force, or there's a force due to the weight that is operating on this spring, and then there's already a restoring force F. But at this point, the spring is in equilibrium, so I can treat this as the starting point for the equilibrium. And if I pull down the mass a little bit further, so that there is a delta x in addition to this equilibrium position, then the additional force, let's call this F0, the additional force F will be minus K times delta x as well. So we can treat this from any equilibrium position. One other thing, so based on Hooke's law, we can of course see that the units of K, or the dimension of K, will have to be the dimension of force over distance. So that will be in newtons per meter. So a force of, a spring constant of 1 Newton per meter would be a spring that exerts a force of 1 Newton for a displacement of 1 meter. That's going to be a very weak spring. More likely you'll see something like 1 Newton per centimeter or 1 Newton per millimeter. 1 Newton per millimeter would be a very stiff spring. 1 Newton per centimeter, or of course 100 Newtons per meter, would be more reasonable for a spring that you might encounter around the house, or maybe in your pen, or wherever you find springs these days. Okay, so springs. The only other force I want to talk about are kind of not really forces. Those are fictitious forces. So why would we talk about fictitious forces in a course about physics? Well, it is necessary because in daily life we often experience these fictitious forces, and we think about them as forces, but they're not really forces. They're in fact caused by changing from one inertial frame to a non-inertial reference frame. So for example, here we have an example, the Coriolis effect, which is the fictitious force that is caused by differences in centripetal acceleration at different latitudes on the Earth. If we go to a higher latitude, we're closer to the North Pole. We're essentially going around the axis of the Earth at a smaller radius. And if we go at a smaller radius with the same angular frequency, then there will be a smaller centripetal acceleration there. That smaller centripetal acceleration compared to the larger centripetal acceleration in lower latitudes shows up in the non-inertial reference frame of Earth as a fictitious force. So it looks like there's a force working on objects when they move towards the north that causes them to accelerate towards the east or to the west, and if they move towards the south, that causes them to accelerate in the opposite direction. So that's a fictitious force that only occurs because we're thinking because the Earth as a rotating reference frame is not an inertial reference frame. Another fictitious force that you might encounter is when people talk about centripetal force. So they think about what is the force that you supposedly feel, or that people think about as pushing objects towards the center. So we introduced the centripetal acceleration because that's really what's happening, and there's something that has a centripetal acceleration as the resulting force. But people will often talk about centripetal force when actually they also mean something different. So in this course, we're not going to talk about centripetal force. We're also not going to talk about Coriolis force because it's not really a force. It's a fictitious force. One way to know that you're talking about a fictitious force is if you cannot identify the reaction force. If there's no Newton's third law reaction force that corresponds to that force. Okay, those are all the forces that we want to talk about for now. But of course, we're going to come back and talk especially about friction some more, and many of those forces we're going to talk about in more detail. About many of those forces we're going to talk about in more detail. So now we get to solving problems in using Newton's laws and drawing free body diagrams, solving those problems with the insight we get from free body diagrams. So there's a couple of steps here, and I'm combining the free body diagram in problem solving strategy that is in chapter 4 with, on the next slide, the problem solving strategy that is in chapter 5, because they're actually very similar. So typically the first thing you would want to do is make a drawing of the situation. You would include all the forces that act on the object. Those are the external forces, and you would draw them as vectors starting from a single point, so representing the object as a point. Then you can split the x and the y components, or split the forces into x and y components, like I did with the tension in the case of the tightrope walker problem. You can draw a squiggly line through the through the original vectors to make sure that you remember not to consider that one anymore. And of course, if there's more objects, then you would have to draw a free body diagram for each of those objects separately if they are different systems that are interacting. For example, when we talked about the two blocks that were against each other in the problem on Wednesday. If there is an acceleration, we don't draw it as part of the free body diagram, but you can draw the acceleration vector separately from the free body diagram. And here they even suggest you can draw it in a different color. So for forces, that's of course problem solving the problems that we might want to solve with free body diagrams is very similar. So start by drawing a sketch, identify the forces, it's the same thing. Define what the system of interest is. So in this case, this is a problem where someone's moving in a grand piano. And so the question is, what is the tension on the hook of the crane that is lifting the grand piano? So identify the forces. So one of the forces here would be the tension. Another force is the force that is pulling down on the hook due to the tension. So that's a Newton's third law force pair. Of course, the system of interest is not the hook. So we don't include the force that is pulling down on the hook. We actually include the tension in the chain that is pulling up on the piano as a force of interest. So we would ignore that force because it's external to the system that we're interested in. Then of course we draw a free body diagram, add the forces, and calculate what it is that we're asked to calculate. So in this case, calculate the tension. So we can apply that to that strategy to an example problem here. So we have a sled that is on a horizontal surface without friction. It's let's say it's ice, and there's no acceleration. That's the setup of the problem. So what will we do? We draw our free body diagram. What are the forces that are operating on this sled? There's going to be the mass, which causes the weight that is pointing down. There's the normal force from the ice that is pushing up against the sled. And then there's the force with which the person is pulling the sled at an angle of 30 degrees. So that means there's these three forces. And again, we can ignore friction here. So there's these three forces on the sled. Yeah, there would still be some friction, but as part of the statement of the problem, it would say ignore friction. We'll come back to friction and how we can calculate friction in the next chapter. So now this force with which we're pulling can be split into an X and a Y component, and to make sure that we don't keep counting that force at an angle, we're going to draw a squiggly line through it so it's clear that that's been replaced by its X and Y components. So that's one example of where we can apply that. How about a slightly more complicated example? So this situation is two blocks are stacked on top of each other. They're on an inclined plane, and I am pulling on the top block, and due to friction between block A and B, there's also a force on block B, right? So what are the forces now? Let's consider this block A as a system. So there's external forces, which are the force due to the tension in this rope. There's the weight that's pointing down. So there's this weight. There's going to be friction from block B on block A. That's going to be preventing the motion of block A towards the direction in which the tension works. So that friction will be pointing in the opposite direction as the tension. And then there's a normal force, which is normal to the surface between block A and block B. So that's going to be normal to also the slope of the incline here. So that's block A. For block B, there's no tension. But there's going to be that third law reaction pair that corresponds to the force from block B on block A that will now be applying on block B as the force from block A on block B. Then in addition, there will be friction from block B, from the slope onto block B that will also prevent motion. Then there's a normal force from the slope here. There's a normal force from block A. That's the Newton's third law corresponding force to this normal force from block B on block A. And then finally, there's the weight that is pointing down. So all of these forces we have to identify and make sure that we know which direction all these forces are pointing in. Sometimes you'll have to think about which direction these forces apply, and sometimes you may have to make some assumption that it's applying in one direction. Then you may end up doing the calculation, and you'll find out that the calculation actually tells you that you picked the wrong sign. So in this case, actually, one question here might be, well, is this friction exerted by the inclined plane on block B, is it actually pointing upwards or should it be pointing downwards? So in this case, so you may have to think about that, and this may be a calculation. It depends on, maybe it depends on the tension. Both cases could, of course, be true, right? If the tension that is applied to block A is very small, you might think that this block is actually almost just resting there. So then the friction is what might prevent it from sliding down. So in that case, the friction would be pointing up. If I'm pulling on block A, and by pulling on block A, I'm also pulling on block B, and it actually is pulling the block up on the slope, then the friction might work in the opposite direction, because it might prevent the block from sliding up on the slope because of that tension on block A. So in this case, it would depend on the details of the problem, but we have to pick an assumption and calculate with that assumption, and then we might find a negative sign for the friction when we solve the problem. So those are things you have to keep in mind, and you already encountered that, of course, on Wednesday in the problem that you prepared. There was one force that came out negative, which means it's opposite in the direction that you assumed it was going to be. So let's actually solve a problem here then, right? So someone's writing, yes, it's a gamble. In a sense, it is a gamble in this case. 50% chance you pick the force in the right direction, but it's not a gamble. What ultimately the answer will be. Ultimately, you will get the sign that forces your arrow to be in the right direction. If you find ultimately that the sign for FB is negative, then you're going to have to change the direction of your arrow, or then at least you'll know that the arrow that you drew originally, you made the wrong guess. You guessed the wrong value, and the math is correcting your gamble. So let's look at this problem now. So we have a mass m2, which is accelerating downwards, and we have a mass m1 that's connected due to with the tension in this rope to mass 1. So what is the free body diagram for both block 1 and block 2 in this case? So take a minute to think about that. You can talk to your neighbors there about what forces are applying, and draw a free body diagram for both block 1 and a free body diagram for block 2. Okay, so let's see. Let's start with block 1 here. So there's three forces operating on block 1. There's going to be the weight of block 1 that's pointing down. There's going to be the normal force due to the surface that's pushing up against block 1. And there's the tension that is pulling block 1 towards the right. And actually, we can draw that here. So this is going to be the force on block 1. You might have included friction. You could have included friction because there might be some friction that is pushing against the motion of block 1. That would have been a fine assumption. In this case, we're going to ignore friction, so there's not going to be any friction in this problem. Similarly, there might be some friction in this pulley. We're going to ignore that as well. In block 2, there's two forces. There's the tension that is pulling the block up, and then there's the weight of block 2 that is pulling the block down. So now we know that there's an acceleration a1 and an acceleration a2. There's something, of course, we can add to our knowledge about a1 and a2. Since these two blocks are connected, a1 and a2 will, of course, have the same magnitude, right? So a1 and a2 could both be equal to a. So the acceleration m1 will be an acceleration a, and the acceleration of m2 will be an acceleration a as well, except it will be in the vertical direction. Also note that the tension here, these are the same values for the tension, right? This is the same tension that is in this rope on the top part. That's the same tension that's in the rope on the vertical part. So if we think about that now, the net force here is the tension. So m1 times the tension, m1 times the acceleration will be equal to the tension. The net force here is m2 times g minus the tension. That will be m2 times the acceleration. So that allows us to calculate the acceleration in terms of the tension, or the tension in terms of the acceleration, right? So let me write that down. So we have that m1 times the acceleration will be equal to the tension. So that gives us the tension. That's from free body diagram 1. And then we have that m2g minus the tension will be m2 times the acceleration. That's what we get from free body diagram 2. So if I use this to plug in the tension, so that's m2g minus m1a will be m2 times a. And so if I solve for a, I'll find that that is equal to m2g over m1 plus m2, or m2 over m1 plus m2 times g. So does that make sense? One thing we'll often do in physics is explore the limits. So we can think of this acceleration as a function now of mass 1 and mass 2. A depends on m1 and m2. But instead of thinking about this as mass 1 and mass 2 as two independent quantities, let's think about this as an acceleration. What happens if m1 is much greater than m2? And what happens to the acceleration if m2, no, that's exactly the same, if m1 is much less than m2? So if m1 is much less than m2, then this is much smaller than this. So then a will be approximately equal to g. Well, if we go back to the situation here, if m1 is much less than m2, then m2 will just fall down as if there's nothing that is keeping it back. There's not going to be any tension in this rope. Okay, here. If m1 is much greater than m2, now the acceleration will be approximately equal to 0, because m1 will be much greater than m2, so we'll get a small number divided by a large number. So the acceleration will be 0. Well, if m1 is much greater than m2, then we essentially have a very heavy block here and a very light block, and the light block won't be able to pull the heavy block. So both of those conclusions actually make a lot of sense. So that's something that always makes sense to do after you solve a problem, especially if it's something that is in a formula shape like this, is evaluate those limits for high values, low values, and see if that makes sense with what you expect should happen. Okay, we'll continue with that next week, Monday, and we'll talk about some more problems. For example, things like this. What happens if those two masses are now at an angle? Okay, that's it for today.